We'll wait for a couple more minutes for people to join and then we'll start at around 6 to 6:10. Uh, Good evening. Welcome to week 6. Just share my screen. Okay. Uh, Welcome to week 6 of bioinformatics algorithms and applications. So, last class we talked about the secondary structures and various algorithms and various techniques by which you can predict secondary structures of a protein using just the sequence information. Now that sequence contains multiple uh, combinations of different amino acids, and the properties of these amino acids, be it hydrophobic or hydrophilic, acidic, basic, or etc. These properties of these individual amino acids are conferred in the proteins also. So if you have transmembrane proteins, you'll have a lot of hydrophobic residues inside those transmembrane regions. If you have a signaling molecule protein, mostly it is going to be the active sites and the regions around the binding sites would be mostly charged and polar residues of the amino acids as well. So today is a little bit more on how experimentally you can determine. So mostly last class we have discussed different computational methods, different algorithms by which you can decide a particular structure of a protein, including, and you can validate that structure using Ramachandran plot and so on and so forth. So basically today we are going to discuss about experimental procedures about how you can get these protein structures, how you can like basically a lot of protein structures have been solved. So how you can get those protein structures from PDB, the protein database, and basically what each of those formats and syntaxes mean in terms of PDB files. Okay, so let's get started. A quick recap. So the primary structures of the like 3 or 4 levels of structure of a protein. So at the primary level, you have just the linear sequence of amino acids, and uh, different combinations of these amino acids are held together by peptide bonds. And on the next level, you have secondary structures, which are local spatial rearrangements. You have alpha helices and beta sheets as the most common of these secondary structures. And the tertiary structure is like having multiple secondary structures and uh, um, like having multiple secondary structures in different regions of the protein, and if you bring them all together and form a single structure, then it's a tertiary structure. So a tertiary structure will have a lot of secondary structures uh, inside the 3D structure, right? So the tertiary or the quaternary structure, whatever, the ultimate 3D model of the protein experimentally can be determined using very well established methods like X-ray crystallography, which is the most common one. Uh, yeah. Uh, in the 70s, 80s, and 60s, X-ray crystallography was the go-to thing for structure prediction, and it is quite accurate. And a lot of Nobel Prizes in different uh, in deciphering different structures using X-ray crystallography has been given out. The most important of them being the DNA structure itself, the double helical structure. The whole model of Watson and Crick is based on X-ray crystallographic data of another scientist named Rosalind Franklin. So and there has been other instances as well. Say, for example, I think 2008 or 9, Professor Venki Ramakrishnan, along with his colleague, won the Nobel Prize for getting accurate structures of ribosomes using X-ray crystallographic data. So X-ray crystallography is slightly expensive, but it is very accurate and it is very well established method of determining structures of different molecules at the molecular level. So the basic idea behind it is basically you have to crystallize a protein. So by crystallizing, I mean is basically so I, going back to class 12 chemistry, it's basically draining all the water molecules out of that molecule so that it becomes a crystal-like structure and there is no water molecule inside, right? So yeah, so there are various ways of crystallizing a particular molecule or a particular compound, but it's not very. In some cases, it is difficult, but in most cases, it is not very difficult to do that. Now, after crystallizing, you form the crystal of the compound or the set of molecules together, and what you do is you shine X-rays on the particular crystal. Now, depending on the edges of the crystal and where there are where there are folds, where there are sharp edges, or where there are other structural elements in that crystalline structure, the X-rays will diffract differently. So diffraction of X-ray is the basic physics principle on which this thing works. So depending on the pattern of the diffraction of these X-rays around the crystal, you can mathematically determine what the structure is going to be. So the diffracted X-ray pattern is analyzed to create an electron density map, which is then interpreted to locate such atoms in the molecule or in the protein. This method provides detailed atomic information about proteins and other molecules in the crystal. However, it works best for rigid proteins, forming well-ordered crystals. This is one bottleneck that you have to keep in mind, that the crystal should be good enough, and like the molecule or the compound or the protein, whatever you are using, they must crystallize properly. And if you do not have that opportunity to crystallize a particular protein or a molecule, it is going to be very difficult to ascertain its structure, because the X-ray diffraction pattern will depend on how the, the the validity of the X-ray diffraction patterns will depend on how well your crystal is formed, right? So that is a bottleneck again. Rigid proteins form well-ordered crystals, while flexible proteins are harder to study due to the requirement of precise molecular alignment. So crystallizing itself is a difficult process. Not I want to say difficult. In some cases, it can be difficult, depending on the type of molecule or the compound you are using. The other techniques that are widely used, the major ones are NMR spectroscopy and the cryo-EM. Cryo-EM uh, in the past 5 years or slightly even more has been uh, a very kind of like up and coming method. Not up and coming. It's a very important method and very widely used method. NMR also, like all the three methods. X-ray crystallography is a little bit of a legacy method, but it is very effective. NMR and cryo-EM are kind of modern techniques, and these are also very effective. So in NMR, the idea is that if you have proteins in solution, it is good for that. It basically involves placing purified proteins in a magnetic field and probing them with radio waves. The resulting resonance form, when the frequencies match, they resonate, and the resulting resonance provides information about the conformation of atoms, which is then used to create a model of the protein structure. NMR is valuable for studying flexible solutions, proteins in solution, unlike other methods that require crystallization, like X-ray crystallography. Large proteins can present challenges due to overlapping peaks at the NMR spectra. We're not going to go details into the NMR method, but you should know about, at least be aware that such methods exist. And the cryo-EM microscopy is basically imaging biomolecules using electron beams and lenses. Cryo-EM is a common method which captures single particles in ice, creating these 2D projection images. So these an electron microscope is involved here. So there's an imaging part to this, right? Uh, uh, which is not part of crystallography or NMR, but there the imaging is not directly of the molecule itself. It is based on so for example, in crystallography, you're imaging the diffraction patterns, not the crystal itself, right? So in these cases, yeah, so it captures these single particles, creating these 2D projection images. And these images, again, if you have multiple of those 2D projection images, computationally it is possible to generate 3D density maps from these 2D images. Now these maps are interpreted by fitting atomic models into them, and recent advancements in sample preparation, detectors, and data processing have significantly improved these methods. Mostly cryo-EM. Cryo-EM is now very effective and very widely used. Uh,
Sir, what are the particles exactly which are seen in cryo-EM?
Sorry, can you repeat your question?
Sir, I'm saying that what are the particles in seen in the cryo-EM?
As in your the image that you're capturing?
Yes, yes, sir.
Okay. So it basically you can image you can image the particle that you're trying to find the structure of. Say, for example, you are doing uh, mm, uh, you are doing cryo-EM of, say, for example, ribosomes, right? So what you are going to get is basically what. Uh, the image is basically would be of individual particles of the ribosome. So uh, individual, what can I say? The individual subunits, if you can say, ribosome will have subunits. So it will be individual subunits of the ribosome, and here you can get the conformations, the basically, so if you have say 8 subunits of the ribosome, you can get that there are these 8 major subunits, and also like the structure of the subunits itself. So you can at that atomic resolution, you can get what are the surface level structures, conformation of these subunits, uh, what are the different conformations, what are the heterogeneity present across different of these subunits. You can also get basically how these are oriented, what are the orientation with respect to each other. So what you're getting is a very high quality electron. Again, these are electron microscope images. So basically what you're getting is an overall density of different molecules that are present in your particular set of compounds that you're trying to get the structure of. So uh, mostly, if you as an example, if you do a ribosome, you're going to get the subunit structures, going to get the conformation of the subunits, and you're going to get the orientation, how they are arranged. So at the high level, at least this is the least amount of information that you can get. I think if you do uh, like if you do more robust imaging, or like with the advancement of uh, advancement of different technologies, I think you can get even higher resolution images for ribosomes. I think there are papers which have done cryo-EM on ribosomes, if I'm not wrong. Let me take a quick look. I think there is a paper for that. Yeah, basically you using cryo-EM you can get the individual. So this is the whole ribosome, right? So the individual subunits, how they are conformed against each other, how they are oriented, what are the different. So this structure of the ribosome subunits from on the surface level, how the structure looks, those information are also you can get. So this is, I think, for one. So ribosome will have like, so 78 ribosome, I think, has a 50s and a 30s subunit, if I'm not wrong. So this is the 50s.
Yes, sir.
Yeah, this is the 50th subunit that has been
So basically, we get the outer image of the
mostly, yeah.
structure.
But yeah, these are, you are not going to get a colorful image like this. What you're going to get is a
Yeah, but
density
we
map.
can get the density maps.
Yeah, yeah.
We can get a darker and a lighter image
Yes,
just
yes, yes. I don't know if
by
there are other
seeing by the
images
density.
shown or not. Yeah, I think
Okay.
we
So,
can. Yeah,
okay, thank you so much.
yeah, you can take a look at this paper as well. Okay. Uh, yeah. So these techniques, I have studied about these techniques, but I do not use them in a daily manner, and it is kind of falls under you can say biophysics, and my field is a little bit farther away from it, so I might not know each and every details of all these things that I'm going to say today. So please bear with me. Okay. So tertiary structure. Yeah. So as I was saying in the previous slide, is like uh, we have seen secondary structure predictions using different algorithms and different uh, computational algorithms and also experimental procedures. But tertiary structure prediction is difficult if you do want to do it computationally. So if you want to say, for example, find what is the tertiary structure of a protein, that you only have the sequence to, like, the only information that you have is this is the sequence of the protein, and you are asked to say what is the tertiary structure. It is a very difficult problem to solve computationally. It is very hard to predict. But there is one easy way to do it, is basically finding homologous proteins. So if there is another protein which has, like, say, 95% match in sequence with your protein, and that the structure of that protein has also already been deciphered and it is known. So you can use something called as homology modeling. I think we'll discuss it in future classes as well. So you can use homology modeling to kind of decipher that if a similar kind of a sequence has this structure, what is the structure of my sequence going to be? Something like that. So again, it's not a very accurate method of doing. So computationally, it is difficult to predict tertiary structures. But again, right now we have a lot of machine learning and deep learning algorithms which can do that. But again, tertiary structures are important, and till now, all the data that we have for tertiary structures are mostly coming from these crystallography methods or other wet lab methods. But again, now we are going towards that deep learning method states where you can predict using deep learning models. Now, the tertiary structure of a protein is basically the 3D arrangement. Uh, the arrangement is determined by the interactions of the side chains of the polypeptide backbone, right? So if you have alpha helices, you have beta sheets, how are these individual secondary structures interacting with each other? What are the kind of bonds that they are forming? And which part of the protein is interacting with which part of the protein? So that becomes important when you are trying to decipher that what the structure is going to be, right? So the basic forces or the basic interactions that stabilize this tertiary structure are hydrophobic interactions, where you have this long set of hydrophobic residues inside your, say, for example, beta sheets, or even in certain cases alpha helices. So those will be tucked inside the protein. So mostly those are going to be in inside the inner core of the protein. Then you have ionic interactions where you have different, so some of your amino acids will be charged and they'll have excess charge on them, and those ions will, those electrons will form, will exert forces on other molecules and also form electrostatic bonds as well. And also not in some cases bonds directly, but it can have ionic interactions. Say, for example, an hydrogen bond. Hydrogen bond is an example of an ionic interaction, right? And you can have like physical forces like van der Waals interaction, and also uh, uh, amino acids like methionine and cysteine will have sulfide bonds in them as well, which are very good at stabilizing this larger protein subunits, right? Uh, yeah. So again, the it the whole tertiary structure will have individual subunits inside them, and uh, this conformations will be based on the peptide's backbone conformation, and it will create distinct regions within the whole structure, which are known as protein domains, right? So these are tightly packed globular structures with a subunit inside them, uh, and it can contain multiple domains. So, in many enzymes, you'll have multiple active sites in that enzyme, in the same enzyme, right? So, multiple active sites, if you have 10 active sites, it will be controlled by 10 domains of the protein, and the residues inside each of them will be very specific to the substrate that they are supposed to attach to. So, it can have a large number of these domains, and yeah, so the number and the size of these domains will be determined by the function and the sequence of the protein polypeptide chain. Right. Okay. So a quick uh, overview I'm going to give about X-ray crystallography. Again, as I was saying that I do not have much experience with X-ray crystallography, so what I'm going to tell you is basically what I have learned while I was studying in my college or like later stages, but I have not used X-ray crystallography directly or even indirectly in my course of my research or my academic career. So yeah, so I'll try to explain from what I understand. Yeah, so the general idea is that we are looking at what we are trying to do is basically form a crystal, diffract extra patterns to that. So again, first a little bit of like you should know what diffraction is. So light diffraction is the bending of light around sharp corners of an object. So that is what diffraction is. And how much is it bending will tell you the amount of sharpness in that corner. So what angle is the corner will can be determined by how much light is getting bent in that region. So there is something called Bragg's law. I don't know if I've included this in my. No, I have not included here, but Bragg's law is basically,
It's
yeah,
a 2D sine theta is equal to n lambda, right?
that is Bragg's law.
Yeah, as
Yeah.
yeah,
So if you have,
my sir mentioned in the class.
yes, definitely. So yeah, that is basically Bragg's law. It tells you based on lambda and the angle, the sine theta, the theta at which the light is falling, at based on the lambda of the medium, you can determine what is the deviation it is going to be. So, yeah, I think a little bit of Bragg's law was there in I think plus two as well. I think yeah, you can take a look at that as well. Yeah, so this is the formula n lambda equal to 2d sine theta. So if you know the wavelength, you know the n and the d. D is the distance and n is the phase or order of reflection, and you can find the theta around it. So if you find the theta, it's basically telling you how much of the of bending is happening in that region, or the scattering is happening in that particular point. So basically, based on theta, you can determine what is the edge structure at that particular region of the compound. Right? Okay. Uh, yeah. So at our level, what we are trying to do is basically find structure of the protein, right? So we want to resolve interatomic distances, which is of the order of 1 to 1.5 angstrom. And visible light is around the wavelength of 500 nanometers. So if you put an electron beam with lambda close to around 0.001 angstrom, which is quite low compared to the wavelength of visible light. So again, electron microscopes, I think in some cases have uh, have this set of you can use electron beam from electron microscopes as even, but like there are specialized machines which can generate these set of waves, right? So yeah, you put a lambda of like around 0.001, and again, you have to assume that the electron is moving at the speed of light, right? So if you put a c value in that equation, the lambda comes out to be around 0.001. Now, electron velocity is less in electron microscopes, so what you need is um, specific machines that can deliver with that speed and that lambda. In some cases, there are specialized electron microscopes which can do this, but again, for these cases, I think we need specific equipment to do this. The typical resolution is around 10 angstrom, but again, I think right now, state of the art, we are at much better place than this 10 angstrom. And again, so this is the uh, level of photons, the wavelength of the photons that X-ray generators generate, right? So our um, uh, target should be around, if you are using electron microscopes or electrons specifically instead of X-rays, sorry. Uh, the ideal wavelength would be something of this order, which is difficult to achieve. But again, using electron microscopes in certain cases you can do. But again, for X-rays, the lambda is around zero point 0.5 to 2.5 angstrom. So again, from a physics perspective, the wavelength is important because if your wavelength is greater than the interatomic distances, what you'll get is basically not high resolution images. Because if your wavelength is so for example, if your interatomic distance is around, say, 1.5 angstrom and your wavelength is of 10 angstrom, it will miss interatomic distances in some cases. It will miss with, the distances which are overlapping its peak and trough of the wave, right? So the lower the wavelength, the better it is, because it, it can increase the resolution. If you lower the wavelength, the resolution automatically gets increased and you have a better image. So the target or the goal is to have lower lambda and which will give you high resolution. Okay, so this is how a general setup looks. So you have a set of X-ray firing machines, which is like around, so lambda is around, yeah, zero point 0.5 to 2.5. In this case they are seeing 1.5 angstrom again. So why is this important? Because the cc bond, the carbon carbon single bond length is 1.5 angstrom, right? If you go above that, you're going to miss this bonds in some cases, so you technically cannot. So this is the range of lambda that we are looking at. So you have a machine that which uh, fires X-rays you on the crystal that you have generated, and this from this crystal it creates diffraction patterns on a detector which detects this whole pattern of diffraction. Now then you refocus this using a crystallographer, and basically you try to uh, from this set of information. So this is a data in itself, right? So the X-ray detector will generate the data of the whole diffraction pattern. Now you can use different tools. There are mathematical models which you can use to convert this data to actually what is the distance between different atoms inside the molecule, different domains inside the molecule, and so on and so forth, right? So this is a general setup of how it looks. So what you're going to find is basically a 3D electron density map, and from that you need to convert it uh, to a uh, to a known, not a known, to a understandable structure. So majorly three steps are involved. First is making of your crystallization protein, which should be around zero point 0.3 to 1 millimeter in size. Uh, they must be ordered in a repeating pattern. Then you aim the X-ray beams at the crystal and you collect the data. And then from the diffraction data, you try to reimagine how the protein is going to look like. So this is how protein crystals look like. Um, I know there are various types of these. So again, this look very big, but again, it is on the range of like 1 millimeter and less. So yeah, yeah. And so this is an actual apparatus of X-ray diffraction. Uh, it is quite expensive, but it is present in a lot of labs in India as well. So there are a lot of people working on X-ray crystallography. So yeah, this is the uh, schematic of the whole setup. So you have a generator which generates the X-rays, and basically from using some charge, it generates the X-rays. Then you have an optical setup in front of that, which uses focusing to focus the beam directly on the crystal itself, because otherwise it is, if without focusing, it'll by in itself create different diffraction patterns, which is not related to the crystal itself. So the focusing of the waves is very important. So you use different mirrors, uh, focusing mirrors to focus it directly on this particular crystal, and then you have this setup which is the goniometer, which is this thing, in between of which the crystal is kept, and just behind that is basically the detector, which detects all the patterns of this uh, of the X-ray. So yeah, this is how an original setup looks like. And after you have gotten, after you have done the experiment, this is the kind of result that you're going to find out. So this is a diffraction image, and these are the dots are basically the spots at which diffraction has occurred. So why these spots are generated? Because uh, the diffraction from crystal lattice, the lattice structures inside the protein, diffract light, and based on that diffraction, these spots are uh, created. And intensity of these reflections actually contain information of the structure of the object inside this crystal. So if you say, for example, a particular lattice is diffracting more than another one, what it means is basically it is much more denser than the other one, and there might be other domains inside that lattice as well. So again, it's not a exact thing that if you find an image and you can directly get a protein structure out of this. You have to process this at multiple levels. You have to understand the data at multiple levels and then try to figure out what the structure is, because there are a lot of caveats involved, a lot of um, confounding factors involved due to because of this pattern. Now, if your experiment isn't well controlled, what you'll find is the X-ray is diffracting off other surfaces in your equipments or in your uh, other surfaces of your equipment, and giving you spurious signals, which actually can hamper your prediction capability of the protein itself. So, yeah. Okay. So again, for determining the structure, you have gotten the crystal, you have put put it through X-ray crystallography, you have gotten all the images. From that, you have used certain mathematical models to derive the structure. Now, how do you store the structure? How do you uh, like relay that information to other people, other researchers of the community? So the one such way to do it is using through PDB. So PDB is the protein database. I think all of you are familiar with this, and it's kind of the biggest protein database uh, currently available. Now, it has a particular file format of which we are going to discuss it. But I'm going to quickly show you this particular protein, right? The ID is 2HSC.pdb. I already have it open here. So what it is basically a zeta zeta transmembrane dimer protein. It is so this is the paper associated with it. So if you go to the paper, uh, just a sec. Yeah. So this is the paper. If you take a look at the paper, they'll tell you how the whole procedure has been managed, what are the different methods they have used, how they have derived the structure. Mind you, this is just one um, a molecule constructed. So this is basically this is zeta zeta transmembrane dimer, right? So uh, just getting that structure is what the paper describes mostly. And like again, when you have gotten the structure, what can you infer from it is another part. But again, so it has used, if you go to the, I'm not sure, uh, yeah, if you go to the experimental procedure section, here they say how they have determined. So this structure is determined using NMR, right? I don't think this is done using extracrystallography in the database also, I think. Yeah, so solution NMR has been used, not extracrystallography. But yeah, it'll tell you what kind of method has been used and give you the paper associated with it, and you can just go through it and see what kind of methods they have used. So this is the structure of this particular protein. Uh, the ID is 2-HSC, and it's a transmembrane protein, right? So this is generally how the page of PDB looks like. So if you can just go and search any ID here, and it will take you to this page. So you can uh, you can uh, try to see the structure in 3D as well. Say, for example, can click on this. Yeah. So if you want to move it around, you can see it how the structure looks and so on and so forth. So this looks like a very interesting one, right? So you have just two alpha helices that are there, and these are all transmembrane domains. So this region of the protein is embedded inside the membrane. So this is not that. This is not protruding outside. So this is a 3D structure, and then you can also see um, the sequence annotations from here. So uh, open in a moment. Yeah, so this describes this is chain A. So these are the different locations. So as I'm moving the cursor on the left hand side of my screen, you can see different regions getting highlighted in the right hand side as well. So it's going to tell you where this particular residue is present, where the basically uh, where in the 3D structure this residue is present as well. And a lot of other information is there. I am not sure of the other ones, but the mutation. So this is one mutation that has been reported in this particular protein. So as you can see, it's on the tail end of the green alpha helix. It's in the. It's not in the transmembrane domain. It's outside the transmembrane domain. A mutation has been reported, and so on and so forth. So and there is a disulfide bridge. See that red mark on the green structure. So basically, it tells you almost everything you need to know in terms of the protein itself. So PDB is a very important resource, and it also tells you basically how many versions of this particular protein has been created. So there has been different versions uh, after the initial release. There have been probably different uh, submissions for this protein after the initial release. Yeah, so this is how the PDB uh, web page looks like, right? Now, if you want to download this structure, you go to download files. So there are a lot of uh, options present. FASTA will give you basically the whole sequence, and these are CIF formats. We are not going to go into details with the CIF formats. The legacy PDB format is the .pdb file. So I already have downloaded this particular file. I've already downloaded this particular file. If you want, you can download it. It's a very small file that you can download. So yeah, so this is if you open it in any text editor. So this is how the file will look like. So there's a header section, there are titles. We're going to talk about what the columns mean. So what is a remark, what is a header, compound, source, and so on and so forth. And the important section, actually like the structure part, starts from here. So model one, and these are the atoms, and these are all the information for the atoms that is required. So these are coordinate. So X, Y, and Z coordinates are present for this particular structure, right? And these are like the amino acid residues, aspartame, serine, glycine, and so on and so forth. So this is how generally a PDB file looks like, and this is very long. So what it is giving is that basically at this particular location there is a leucine. These are the X and Y coordinates of the leucine molecule, right? So it's a very big file. I'm not going to scroll down to the bottom, but this is generally how it looks like. There is the .zip file as well, which are the newer formats. So if you go to this, uh, yeah, the header and the comment sections are different. So here, this sections are different. There is a different set of information that gives the whole name of the paper, and all of that information is also given, type of protein, and etc. etc. So yeah, a lot of information given here. But again, the main structure uh, starts from here. Yeah. So no, no, sorry. The main structure starts from here. So atom, and then this is almost as similar as the PDB legacy format as well. So yeah, the main structure starts from here, and it's similar to what we saw earlier. Okay. So yeah, now we're going to discuss um, different annotations inside the PDB file, what each of these annotations mean, and how you should interpret them. So it begins with a header section, as I was showing. So this is the yeah, this is the header section. So it describes the protein and basically when it was submitted and the ID of the protein. It's the first line that you're going to see, right? Uh, so yeah, the header will look like this sometimes, and basically what it means, it is telling you is it's a membrane protein and when it was deposited and what is its PDB ID. Uh, the position or the columns are important here because each of them are basically tab separated. So header is tab separated to membrane, then tab separated protein, tab separated the date and the ID itself. So yeah, I'm not going to go into much details, but the header line looks like this, and these are the information that you can get. The compound record is basically it is also description of the protein itself, but uh, it is like divided into different lines. So it starts from here. So this is the molecule ID. This is the first line. The second line describes the molecule, T cell surface glycoprotein CD3 zeta chain. There are two chains A and B. Then again, the fragments is it's a transmembrane region of for this particular set of residues. What is the synonym of this, and what is if it is an engineered molecule or not? So it's basically describing the compound itself. So it's called the compound record. First you have the header, then you have the compound record, which describes the compound in different lines, and the line numbers are given in here 1, 2, 3, 4, 5, 6, like that. So yeah. Then comes the remark record. So it can have hundreds of remarks. So it's similar to how we remark in a code file in R or Python or in any other coding languages. We use a hash and then we write a remark. Here also it's similar. Uh, it starts with a number which simply identifies as a remark. So, for example, remark 3 starts like this. So these are, I think, name of the authors that have deposited this data and so on and so forth. And so the remark numbers are also jumbled up. So the first sections, the header, compound, and remark, are mostly describing the protein, what is known about the protein, the method by which this structure has been gotten, the date, and basically the people who have submitted this data. Now there is one primary structure section. It might not be in all files, but I think it is there in this particular file. Mm, Just a sec. Mm, Yeah. So this is the sequence. So the sequence uh, is basically it is telling you the sequence of the amino acids there. So it is again like it is starts with the serial number that goes up by one in each line. So what it is meaning is basically it is continuation. Sorry, it is a continuation. So after phenylalanine, there comes isoleucine, then tryptophan, so on and so forth. After valine, there's leucine. After aspartic acid, there's another aspartate. So on and so forth. So uh, so A and B are basically the two domains of the protein, and these are this is the total sequence of A, and this is the total sequence of B. So um, yeah, uh, this describes the primary sequence of the protein itself. Now, the secondary structure is the one uh, that we are interested in, and basically PDB is used for. It gives you information of the structure of secondary structure of the protein, specifically the helices and the sheets. Uh, there is a very well defined. So in PDB, sorry, yeah. So in this particular section, this is one section, and there is another one, I think. Uh, yeah, these two pages. So I'm going to put this link here. So if you want to learn more about PDB formats, because if you want to work in biophysics related things, specifically proteins and all, PDB is something that you will have to encounter almost every day. Sorry. Uh, yeah, this is the other one. You can take a look at these websites. Okay. Okay. Yeah, one thing that can happen is the secondary structure determined by different algorithms will can be different. So and these algorithms always will not agree. So you can have different versions of the same molecule itself, and also like you can have a consensus version of the molecule also. So if you have conflicting information, in most cases it is not displayed, meaning the whole protein will not be displayed if there are good conflicting information about how the structure is looking from different sources. But it can be an ensemble of the set of structures given to PDB as well. So that is also there. Now, the the secondary structure or the actual the structure of the protein is given in this particular model record. So it starts with the model number as I showed in this particular uh, case. So it starts from here. It's a model. This is the first model number, and these are the atoms of which protein, of sorry, which amino acid, and so on and so forth, right? Uh, so yeah, it looks like so yeah, so typically molecules or proteins determined by crystallography will have only one model. In many cases, you can find multiple of these models. And this was determined by NMR spectroscopy. So there are several protein conformations that are consistent with the NMR data. And this is how the data looks, right? So yeah, so an atom is a single line record and it occurs multiple times, each for one atom for each model. So in this case, there's only one model. So in this particular entry, it tells you that uh, yeah, atom one is named as Ca, which is part of the aspartic acid residue in chain A, and its residue ID is -3. So this is what this first set of numbers are telling you. Then we are given orthogonal coordinates of the atom. So these are the x, y, and z coordinates. So x, y, and z coordinates, this in space, how where they are. After the atom's coordinates, we have two special numbers, the occupancy and the temperature factor. So first is the occupancy and second is the temperature factor. Occupancy is basically the proportion of time that the atom spends occupying a particular position in terms of the crystallography or the NMR data that you have generated. Because if you have uh, a, a flexible molecular region which is conformationally changing through time, so there the occupancy factor will be lower compared to other regions where it is a very rigid molecule. There is no flexibility at all. Uh, in this case of this particular protein, all of the atoms take only one conformation, so their occupancy is 100% always or 1. The B factor, on the other hand, is basically known as the temperature factor, and it tells you how much of an atom is nearing or vibrating around its central coordinate in the crystal structure. You can think of this as a standard error metric. So you have the molecule atom positioned in a particular coordinate of XYZ. What is the error associated with that? So how much of it is like vibrating and slightly moving around? So that is what the temperature factor or the B factor is giving you. It is kind of giving you the standard error of that particular of the atom being at that particular location. So these coordinates will give you the average position of an atom. The B factor describes the uncertainty again, which is the standard error basically. Uh, if the B factor is low, the atom is very stiff, and if it is high, the atom is floppy and poorly defined. It might be vibrating heavily due to thermal energy, uh, or its entire loop is it's attached to be attached to might be swinging around, right? So how much of it? So basically, it is tell you how much vibration is going on and if the atom is still or not, right? So again, this is another. I think this is a different file, but again, it is doing describing the same thing. So this is the atom number, this is the atom name, which is this giving, this is the residue of in which the atom is located in. This is the number for the residue. These three are the XYZ coordinates in this case, and then you have the occupancy and the temperature factor. And uh, in terms of uh, so there's an error also involved in this set of coordinates that are being given. So if you so in terms of the error also, they are defining if it is high, low, or anything else other than that. So this is in general how we define or how we generate and store the data for these complex 3D structures of these proteins. Yeah, so again, this is the fractional occupancy. Again, we discussed this, and the B factor is basically these are two distributions shown. So the purple one is basically both of them are normal distributions. The purple one has less variance or spread, and the black one has more variance or spread. So in this circle that is showing, so if your B factor is coming from the purple distribution where there is very less variance, so and very close to the lower set of values. So if the atom is still in its place, like it is not very much vibrating around. But if you have a lot of variance inside your B factor, the boundary of the vibration or the boundary of the variability increases to the black one. So again, it intuitively it is telling you if it is stuck in that location or is it slightly moving around or not. So that is what it is telling you. Okay, coming to tools for visualizing this particular proteins or this data formats, the most common of them is PyMol. I think PyMol is now under Schrodinger. Schrodinger is basically the paid better version of PyMol, you can say. But again, PyMol is very useful for people who are going into the field as a newcomer. So to understand the structures and do basic shell scripting and Python scripting, PyMol is great and PyMol is very good. So if you have a protein, it will show you like this. This is a whole 3D space from which you can move around the molecule and the different uh, parts of the molecule even. And it represents the cartoon representation visualizes secondary structures, helices as spirals, strands as arrows, and so on. So I hope you can see these arrows. These arrows. So these arrows are basically beta strands, right? And then the spirals are your helical structures, the alpha helices. Uh, yeah, you can do a lot of things using this. So for example, you want to find the distance between this particular alpha helix here, the red alpha helix here, and the green alpha helix here. You can find distance between this. So RMSD is basically that root mean square distance, which is the Euclidean distance. If you have x, y, and z coordinate, you can find distance between any two atoms inside that protein. So you can do it in binary even. Okay, now we have different databases and different types of classifications of proteins based on the structures of these higher level molecules. So high level structures, not at the level of secondary structure, which is alpha helix or beta sheet. Let's give me a minute. I'll be back. Sorry for that. Okay. Mm, yeah. Now we come to different possible classifications of these proteins based on these structures and also databases that are formed based on this. So SCOP is one such classification uh, parameter. So it is structural classification of proteins. So these are classified manually, taking into account both the structural and evolutionary relationship, and they give 7 classes of proteins. So one will be all alpha, one will be all beta, and there will be alpha beta, beta alpha, and alpha plus beta. So basically, different combinations of these alpha and beta secondary structures, and what is the tertiary structure actually made of, right? Uh, the principal levels of hierarchy in this classification are fold, superfamily, and family. So family is basically which is having clear evolutionary relationship. in general, they take 30% pairwise residue identity to be considered into the in a family. Superfamily is basically probable common evolutionary origin. They might have low sequence identities, but structural and functional features suggest a common evolutionary origin. And fold is basically the structural similarity, having similar major secondary structures in the same arrangement and with the same topological connections. They are classified into the same fold. Right? So this is SCOP. Another classification method is CATH. So in this case, it's a hierarchical domain classification of protein structures in the Brookhaven protein data bank. Only NMR structures and crystal structures solve to resolution better than 3 angstroms are considered. So these are like the best possible structures that are available. And here there are like 4 major levels of hierarchy. You have class, you have architecture, you have topology, which is the fold family, and then you have homologous superfamily. Uh, so this is the basic example of that. So you have these fold families. So you have alpha, alpha plus beta, and beta. So in alpha plus beta, you'll have different types of these tim barrel, sandwich, roll. So how these alpha and beta sheets are arranged with respect to each other. In sandwich, you can have different. So in sandwich, these are the two examples of sandwich folds of alpha and beta. So this is another type of classification. Okay, so this is basically distinction and similarity between these two set of classifications. So they both have classes. Architecture is present in cat, not in SCOP fold. There's a similar one in cat, which is the topology. Homologous superfamily is not seen in the SCOP. In SCOP, we see superfamily and family, which is superfamily is basically not good sequence similarity, but there is a good amount of similarity in the structure and the function. And yeah, that is not considered in the cat. Uh, and another thing that the other things that are present in both are the family, which is basically sequence identity, and domain of the protein itself. But the classifications uh, of these two distinct systems can classify same proteins into different modules. So, for example, human lysozyme. So it has 31% alpha helix and 8% beta strand. Cat classifies it as all alpha due to high alpha helical content. SCOP classifies it into alpha plus beta due to presence of greater than 5% beta strands along with alpha helices. So the classifications might differ based on the systems used, but yeah, we should know uh, which one does what. Okay, so these categories are all alpha, all beta, alpha, beta, and so on and so forth. So one such example is like all alpha proteins, right? So the core of the protein is composed of all alpha helices, and it has two major subtypes in cat classification: the orthogonal bundles, and there's another one I have not put a classification here. So basically, these are bundles where you have the so these arrows are your beta sheets. The again, the spirals are your alpha helices, and these are mostly at orthogonal angles to each other. And the protein described here is the beta domain of the RNA editing enzyme ADAR1. So this is the idea of that enzyme. Okay. Then you can have beta proteins, which are mostly your beta sheets. So these all the arrows are your uh, beta sheets. So these are basically typically an anti-parallel beta sheet. There are many types of these, including single sheets, rolls, beta barrels, clams, sandwiches, propellers, etc. Beta barrel, we described one beta barrel protein, I think, in the previous class or the other class. But yeah, so just to give you an idea about how different kind of conformations can be possible and how these are classified into one or the other, right? And these are like combination of alpha beta proteins. uh, Many beta alpha beta motifs. So you have beta sheets, then you have alpha helices, then again beta sheets. So this kind of motifs with mostly parallel beta strands surrounded by alpha helices. Again, these proteins have many variants, including the alpha beta barrel. So these are the two most common ones. So both are sandwich. So this is a two-layer sandwich, which is a HIV core protein, and this is the human biliverdin 9 beta reductase, which is a three-layer sandwich. So there are three layers. I know it cannot be seen from this angle, but trust me, there are three layers of these alpha beta alpha or beta alpha beta uh, motifs in the proteins. Now we come to another important concept, which is basically contact maps, right? So in contact map is a 2D matrix. Again, this is very similar to if you remember dot plots when we are discussing sequence similarities. So the idea is similar, that if you have a certain similarity or a certain proximity, you put that as a dot. If that condition is not fulfilling, you do not put anything there. So that is what a similar type of concept is the contact maps, right? So it's a 2D binary matrix representing 3D spatial distances between residue pairs. So basically, between residue I and J, if they're closer than a predetermined threshold using specific atoms, the matrix element is a dot. Otherwise, it's a blank. So similar to what the dot plot does. If there is a similarity, there is a dot. If there is a mismatch, there is nothing. It's blank there. So the map will be a symmetric matrix as contact is bidirectional. So if I is connected to J, J is also connected to I. Interresidue contacts are categorized by how far apart the contacting residues they are there in the primary sequence. So if you have contact less than by three, so separated by less than three residues, that is short range, medium range, from 3 to 4 range. But if you have greater than uh, 4 amino acids between your contact of amino acid 1 and 5, then it becomes long range. So anything greater than 4 is long range, and it is so the medium range is a characteristic of alpha helices. The long range is a characteristic of beta strands and tertiary folding as well. So it is shown here. So you have uh, this is medium range. See, medium range, there's a thicker line here. So this is mostly alpha helices. You have a long range here. So these are mostly beta sheets, and these are anti-parallel. So these are moving uh, opposite to what, so the opposite diagonal, so that's an anti-parallel beta sheet, and so on and so forth. So you can get all this information using contact maps. Similarly, how we got information of alignment and sequence similarity using genomic dot plots or protein dot plots. So now, again, based on structural classes, they show distinct long range or contact preferences. So all alpha helices or alpha proteins will have very few long range contacts, mostly medium range. All beta proteins will have prominent long range contacts, all often separated by 11 to 20 residues, and alpha beta proteins show a peak in contact separated by 21 to 30 residues, example in non-terminating Tim barrels. So yeah, that is fine, but I want to make you understand why alpha helices will have mid-range. Like, it is intuitive that if you assume the beta sheet is a zigzag sheet of uh, sequence of amino acids. So a amino acid which is very far away in the sequence can come in contact with the amino acid uh, uh, with your amino acid of interest, because the beta sheet is basically the sheet going from this direction, then again the sheet folding and coming to this direction. So if you have residues towards the end of the sheets, they are going to most likely come in contact and stay very close because of the sheet structure of beta. So if you have a beta sheet, the thing is you have much more longer contacts because the packing of the sheet is such that residues from very far away can come in close proximity. But that is not the case for alpha helices because it's a spiral. It will only have medium range contact because it cannot fold like a beta sheet and bring the residues at the extremes close together. So for beta, it is much easier to have long range contacts. For alpha, it is mostly short range and medium range contacts. Right. Okay. So yeah, this is I think the final topic that we are going to discuss for today. So uh, this is basically solvent accessible surface area. So if you are trying to, uh, yeah, go ahead.
Sir, so alpha and beta together, alpha beta proteins have long range contact.
Yeah. So it will depend on the structure. So inside the alpha, so here I'm saying that alpha beta proteins will have very long reach contact, but uh, if you, it is going to be true if you consider the alpha an amino acid in the alpha helix contacting the amino acid in a beta sheet, because if you have both alpha and beta secondary structures, one is going to fold on another. So the alpha, in some cases, the alpha one of the alpha helix will be very close to another beta sheet. But what I'm trying to say in just in terms of alpha helices and beta sheets are basically if you just have beta or just have alpha, in case of the alpha, the contacts are very in the medium range, because there is no folding as present in beta sheets, which can bring very farther away residues close together. But in beta cases, it can happen because you're folding the the so the polypeptide chain. Basically, you are folding it multiple times in a parallel or anti-parallel manner, which can bring very farther away residues close together. But when you have this combination of alpha and beta, one residue in the alpha helix might be in long range contact with one residue in the beta sheet, because the alpha helix has folded on the beta sheet. Now, the amino acid residue present in the alpha helix is very far away from the amino acid residue present in the beta sheet in, in terms of its sequence information. But since the folding has happened on one on top of another, the alpha helix residue is very close to the beta sheet residue. That can happen. So I hope I have made this clear.
Yes, sir. Yes, sir.
Yeah. Okay. Now comes the part where we check for how soluble particular proteins are, and how you can mm, uh, yeah, how you can basically use a solution to um, use a solvent to for this particular set of proteins, which are the solutes, right? So this is known as solvent accessible surface area. So the solute is represented as a set of interlocking spheres, with each sphere corresponding to an atom-specific van der Waals radius. The solvent molecule is typically assumed to be a sphere of water with a radius of 1.4 angstrom, reflecting the natural aqueous environment of most proteins. Uh, and you can compute this soluble solvent accessible surface area. Again, like I'm before going, like, knowing what it is, um, you should know why you you need solvent accessible surface area, because it is going to tell you uh, how how this particular protein is going to solve in a particular solvent, how it is going to mix in a particular solvent. If in the cell there is a cytoplasm has some solvents, will this particular protein uh, mix in that solvent? So this kind of information is given by solvent accessible surface area. If you have high accessible surface area, it is more likely that it is going to be mixed in the solvent, and if you do not have high accessible solvent area, so sorry, surface area for the solvent, it is not probably going to mix. So you can determine this using the structural analysis, and seeing if you determine the structure, it is most probably so if you determine the structure, uh, it is probable that you can find what is the surface area that is exposed to the solvent, but without the structure, it is very difficult to understand. So there are algorithms which predict how much of the surface area is available for the solvent. Uh, uh, and what type of residues are there. So again, that is important. So if you have non-polar residues, probably you'll need an organic solvent for that. But if you have polar residues, water is enough to mix it, right? So these are the different computational methods. I am not very aware of these computational methods. I got the information, I've put it in the slide, but yeah, if you are interested, please take a look at this. I am not very aware of these set of algorithms and programs, so apologies for that. Okay. Okay. So if you if you have the whole surface area, you can actually find what is the percentage of the protein actually present in the surface area and what is the percentage of the protein that is actually available for the solvent to come and bind and solve its work. Okay. So if you have absolute values of these from these algorithms or from experimental data, it can be misleading because different amino acids have naturally different sizes and atom counts. So the surface area, so if you have amino acids which are having larger side chains in the solvent accessible surface, the surface area will naturally increase, but it is not telling you, but it is artificially getting naturally getting increased, but it is not actually telling you anything about this solute capability of the amino acid. Okay, how much will it actually mix in the solution? Because that is only one amino acid. The space required by that amino acid is much more than say a glycine or something, the smallest one. So if you have different amino acids, the surface area estimation might be misleading because again, just by the size of the amino acid present itself. So you need to correct for this bias because you what you want to know is the number of residues proportional to the number of residues that are present in the surface area. You do not want surface area as a metric. You just want to see how many residues are present or how many important residues are present in that area. So for to correct for this bias, they normalize into percentage accessibility. Uh, what it is basically the ratio between the computed value of the surface accessible area from the 3D protein structure uh, to the that is the numerator. The denominator is the accessibility area of the same residue in a fully extended unfolded state. So yeah, that is the percentage accessibility. So it kind of mitigates the bias of the length or the size of the amino acid itself. Uh, yeah, so if you have less than 5% accessibility, it is mostly buried. If you have between 5% and 20% accessibility, it is partially buried, and more than 50% accessibility, it is located on the protein surface. And this is how you calculate the buriedness index. So it is basically in the numerator, you have the number of buried residues of type I, and say, for example, polar. The number of polar residues uh, and number of total residues of type I. So basically, in the surface, how many polar residues do you have? And in the whole protein, how many polar residues do you have? So that is the buriedness index. So it is highly correlated with the residue's hydrophobicity. So if you have highly hydrophobic residues, it is automatically going to be buried, right? So it is highly correlated. And how do you calculate the free energy is basically the ratio of the internal to the external number of residues of that particular type. So for example, polar residues, how many are externally situated, how many are internally situated? You calculate this F, and you use this to calculate Gibbs free energy, which is delta G negative RT log this expression Fi, right? So that is how we calculate the free energy. So the idea is that if you compare two different structures, right, and you have two different buriedness residues, buriedness indexes, and you can calculate the Gibbs free energy for a particular set of residues, the the state at which the Gibbs free energy is lower is more preferred than at which it has a higher Gibbs energy. So that is given as well. Okay, yeah. So if you have this long range contacts and short range contacts and whatever and whatnot, so I think we have discussed this. So if you have greater than 10 or 12, it's a long range contact, and if you have lower than that, it's short range and mostly alpha helices. And you can have multiple contacts as well. So it identifies key stabilizing residues by highlighting those that maintain simultaneous long range contacts with at least four other regions. So yeah, those are important as well, right? Yeah. So yeah, my discussion part comes to an end here. If you have any questions, we can discuss that, or we'll move on um, to the assignment questions. Again, just
Sir,
yeah,
we had a prob.
yeah. Last week का problem, na? Sorry, you are muted. Are you saying anything?
Sir, we had a problem in previous lecture, question number 4,
Yeah. I
but it was uh, discussed by Sir Sunanda sir
Okay. He
in
discussed it.
last lecture.
Okay.
But if the student have, in any student have who have not attended the previous lecture, can say that if they want to know. But it was discussed in the Monday's lecture.
Okay. Then it's fine. Actually, I tried contacting uh, Sir or his TA. I could not. I have the answer, but I think if he has discussed that, it's fine. I'll not go through it again. But yeah, if I get one thing I'm trying to get is basically good, uh, like what you say, detailed answers of each of the assignment questions. If Sir has it, because these are older assignment sets, right? If we already have an answer key to this or like a detailed set of answers to this, if I already have that with Sir's explanation, I will definitely bring it up. But till now, I don't have that. So yeah. Okay, then we'll discuss this week's set of questions. We'll come back to anything if required later. If somebody has a problem, you can definitely bring it up. Okay, so again, just to say, if you have any questions here in this set, sorry, okay. Yeah, this was the question that had the issue, right? So yeah, I was doing this. Anyway, for today's lecture, if you have any questions, so I'll be very honest with you. I'm not very familiar with this side of the field or course of this of this set of uh, concepts. I am teaching you or I'm telling you on the basis of what I had learned in my courses or my college or like what I have studied recently for giving this lecture is the information that I have. I personally have not um, been accustomed to any of these data. I just have studied it in my coursework or some time ago. So yeah, if you think I did not do a good job in describing any of the concepts or any of the topics, please let me know. I can come back again next week to that topic by preparing myself a little bit better because I am not from this particular field at all. So this is also quite not new. I've studied all these, but I have not done hands-on anything of this sort before. So if you have any doubts or any concepts that you think I did not explain properly or anything, you can just let me know. I'll come back with a better prepared version in the next class. Okay. Overall important topics. There is going to be one session at the end of the 12 weeks. So there will be 1 2 hour session, which is after. So this kind of sessions will be there will be 12 of these because there are 12 weeks. And after this has completed, there will be one session of 2 hours where we'll discuss start to end mostly all the important topics that are covered in this course. So that will be there for from both my side and my colleague's side who is taking the other I think he's taking on Monday. So from both of our side, I think there will be one extra session to discuss everything miscellaneous from the course. But other than that, it is like every week that week's topics are discussed. So yeah. Okay, then we'll move on to the questions. Okay, let's see. Yeah, so again, in some cases, what can happen is I saw another question similar to this where they have given ionic bonds or something like that as an option. So instead of hydrogen bond. So uh, be careful about the terminology of the bond because a lot of terminologies are used interchangeably. So you might not get exactly the option that you're expecting. It can be written in a different way also. So I would ask you to keep that in mind as well. Okay. Yeah, yeah, yeah. Today's questions are mostly easy. Yeah, Pymol. Yeah, so if you are interested, do try Pymol because Pymol is very easy to install and very easy to use. And scripting also, it is very easy to use using Python. So if you're interested, definitely try your hand at Pymol. And you can download any PDB structure as I showed, and download and use that file and visualize that file, find distance between different residues, find interactions between different residues, and so on and so forth. It is very interesting. Do try Pymol. It's free. Sorry, which one? Previous question, is it? This was Pymol, option B, and the first question was hydrogen bonding. First question was hydrogen bonding. It's non-covalent interactions to form protein secondary structures. So you have these uh, carbonyl atoms, right? So C double bond O, which is polar in nature because of oxygen, because it pulls the electron towards its size, and also in terms of the amide bond as well, NH, that is also a very polar bond. So hydrogen bonds form between CO and NH, the H of the amide and the oxygen of the carbonyl form weak hydrogen bond. So I hope that makes it clear. Okay, yeah, this is SCOP, which is structural classification of proteins. I mean, we discussed this. So yeah, moving on. Yeah, I see a couple of B's in A. The answer is that of a water molecule, which is 1.4 angstrom, not 1.2. So for SA, they generally use the probe radius for a water molecule, which is the solvent, which is 1.4 angstrom. So not a 1.2, it is going to be 1.4. So basically, the probe radius will tell you if it is actually going to be solvable or not. So they'll check the probe radius of 1.4 angstrom across the whole surface area and uh, basically check which sections are accessible and not. Do not have any answers yet. Wait for a minute. Okay, I see a couple of B's. Okay, 3 alanine, 2 alanine, so 4, 7, 1 3-alanine, 1 glutamate, 7. Okay. Yeah, I think the answer is not negative one. I think it's two answers only. I think it's 6 if I'm not wrong. Yeah. So 3 alanine is 3. Okay. 2 valine is 2 times 2 4. 1 threonine is 1 times -1. Okay. 1 glutamic acid. Yeah. 1 times -2. Okay. 2 tyrosine. 2 times 1. Yeah, I think it's 6. Uh, did I miss something? Oh, I see a couple of negative ones. I think this is correct. Like, it should be 6.
Sir, it was a guess from my side. D was guess.
Okay. Acha.
And I am also took tyrosine as R, which was arginine.
That is the thing.
I remembered it vividly.
Yeah, remember we discussed in the last few classes that you need to remember the single letter codes because in most cases you'll have questions like these where these questions are not actually testing your knowledge in terms of hydrophobicity or anything, right? This is only testing your knowledge if you can identify the single letter codes for amino acids. So in many cases it will be that situation. So you need to know the single letter amino acid codes. Yeah. Okay, moving on. This should be easy. Yeah, that's correct. So if you have, I think anything greater than 10 or 12, it is flexible. So yeah, 75 is highly flexible. Uh-oh. Just give me a minute. I think I forgot to copy the contact map here. Just a sec. Okay. This is easy. This should be. I've been asked which is the basically long range contact. It just should tell you in terms of the position only. Yeah. Yeah, that's correct. Because you see, the second leucine is in contact with the 10th serine. So that's the long range contact that you're looking for. So yeah, it's second leucine and 10th serine, which is like 8, which qualifies as the long range contact. Yeah. Okay, I think it's B. Yeah, yeah. I think the higher the values, the more probable that they are located on
Sir,
this.
sir, this question was actually the same question was done in yesterday's class, and it was D. So,
It was D.
so it's another. Yeah, sir said it was Z. I actually did answer B in yesterday's class, but he said it's B.
Just let me check one thing.
As
Just a sec.
yeah.
Mm, My understanding is also like if you have higher values, it's more probable.
Sir, actually, I did answer wrong. I don't know. I expected that the answer is B. I also
So in
answered
the
B
answers
yesterday.
provided to us by NPTEL, the answer is B. It's not D.
Uh, it's not. It's D.
It's B. B for Bombay.
Oh, it's a B. Okay.
Huh.
Sir, in previous classes, yesterday's class, the same question. It's it's exact word to word.
Okay. But like it is the answer is given as B, and my understanding is also B is the correct answer. I'm not sure about D. D is basically the opposite answer of B, right? That you have lower value.
Yes, yes, yes. Yes, sir.
Yeah, my understanding is that higher values would be closer to the surface. So, and in the answer sheet also it is given as B provided by NPTEL. So, not sure. You can bring this up in the next session when he has maybe
Okay, sir. I'll
once.
do that.
Yeah. Uh,
He said the lower the solvent accessibility, the out on the outermost it is.
my understanding is it's the opposite. Uh,
Uh, okay, sir. Okay, sir. I'll bring it up in the next class.
also, let me check. Uh, solvent accessibility. Mm, Uh, Google is saying residues on the surface have high SASA. Um, yeah, I'm not sure about the opposite thing, so uh, you might want to ask the reason for his answer because where I'm seeing that the higher
Okay,
the
sir.
values that you have, the more on the surface probable that you're on the surface. So yeah, the answer
Okay,
has
sir.
also been given like this. So yeah, you can ask him next class.
Okay, sir.
Yeah. Okay. So these questions have already been discussed yesterday. What?
Not the same, not all of the question, just the previous one.
Okay. Here you have to use the uh, Gibbs free energy formula, del G equal to negative RT log of the ratio. No, I think somebody answered A. You're close, but you have to look at the uh, unit. It's kilocalorie. Yeah, yeah, yeah. It's basically you have to keep in mind the unit since it is kilocalorie. If you divide by 1,000, so it's yeah the second option. So basically, yeah, you have number of buried residues and number of residues on the surface. You take a log of that and negative RT. If you solve this, this comes to around negative 2 point, negative 0.242 kilocalorie. So this will be, if you calculate like this will come with calorie per mole, but you have to keep in mind the unit. So kilocalorie. Fine. Okay. Yeah, that's the answer. The thing is, you have to calculate the Euclidean distance for prob most of them. Sorry, for all of them, and I think this will come as the lowest. And the important thing is these are oppositely charged amino acids. So um, this has the potential to form electrostatic bonds, and also they are relatively located close together if you calculate the Euclidean distances. So yeah,
And sir, I just saw the x coordinate. Compare the x coordinate with the y coordinate and the x coordinate. Two z coordinates, two y coordinates, and two x coordinates, which had the lowest distance. Uh,
yeah,
then I
yeah.
give the answer.
Yeah, but also you have to keep in mind if they're asking for electrostatic bonds, there should be a potential for electrostatic bond. If these are like hydrophobic residues, or these are, say for example, residues that are not polar, or that are like similarly charged, both of them negatively charged. So there is not no possibility of electrostatic bonds, right? So it can only happen if they are oppositely charged and also closely in close proximity of each other. So this fits the bill. Okay. Yeah, that's all from my side. If you have any questions. And yeah, before I end the session, just want to give a quick um, thing. So this Saturday is basically open day for IISc. So if any one of you are in Bangalore, so what we happens in Open Day is basically the institute opens to the public, and we showcase what we have been doing through models, through posters, through different kind of uh, presentations, and all of the departments in IISc showcase their work, and it's quite an enriching event if you want to learn about the types of research that is going on in different domains and so on and so forth. So if anyone of you are in Bangalore, uh, and it's open to all. So if anyone of you are in Bangalore, please visit ISC on Saturday. It will be an enriching experience for you. So yeah, thanks. Ah, if you have any questions, uh, please ask. Okay then, if no questions, and thank you for joining. We'll close the session here. Uh, See you next Tuesday. Okay.
Thank you, sir.
Yeah. Thank you. Bye bye.